Welcome to Mind XY, your channel for logical thinking and puzzle solving. Hey everyone, have you ever seen a problem that seems impossible at first glance but hides a beautiful, simple solution? Today, we're diving into a challenge that combines triangles, lines, and some mind-bending geometry. Are you ready? Our challenge starts with a right-angled triangle, ABC. We drop an altitude, AD, from the right angle to the hypotenuse. This creates two smaller triangles, ABD and ACD. We find the incenters of each of these smaller triangles. We'll call them I sub 1 and I sub 2. Finally, we draw a straight line connecting I sub 1 and I sub 2. This line cuts the original legs at points K and L. Our mission? To prove that the area of the large triangle, which we'll call S, is at least double the area of the small triangle. That's right, S is greater than or equal to 2t. Now, looking at this, your first thought might be, maybe the little triangle AKL is just a smaller, similar version of our big triangle ABC. If that were true, the problem would be much simpler. We could just find the ratio of their sides. The little triangle AKL is not similar to the big triangle ABC. Why? Because the line from our incenters cuts the sides in a unique way that doesn't preserve the angles of the larger triangle. This line is special, and we can't assume a simple relationship. So we have to find another way. A better way, a secret way. But the solution lies in a stunning geometric secret. The points K and L aren't just random points. They are special. The line AI sub 1 perfectly bisects the angle BAD, and the line AI sub 2 bisects angle CAD. Because of how angles work in these similar triangles, this simple fact has a massive consequence. The length of the segment AK is exactly equal to the length of the altitude AD. And the length of AL is also exactly equal to AD. So, the genius of this puzzle is that AK equals AL equals AD. Now let's put it all together. We need to prove that S is greater than or equal to 2t. Starting with our area formulas, that means we need to prove 1/2 AB times AC is greater than or equal to 2 times 1/2 AD squared, which simplifies to AB times AC is greater than or equal to 2 times AD squared. We know that for any right triangle, the altitude is related to the sides by the formula. AD equals AB times AC divided by BC. Let's substitute that in AB times AC is greater than or equal to 2 times the quantity, AB times AC divided by BC squared. Now, a little algebra to simplify this. 1 is greater than or equal to 2 times AB times AC divided by BC squared. BC squared is greater than or equal to 2 times AB times AC. And here's the beautiful final step. We know from the Pythagorean theorem that BC squared equals AB squared plus AC squared. Let's plug that in. AB squared plus AC squared is greater than or equal to 2 times AB times AC. This final inequality is a famous one. You might remember it as a version of the AMGM inequality. It's always true because it's equivalent to the quantity AB minus AC squared is greater than or equal to 0. Since a squared number can never be negative, this statement is always true. And with that, we've proven that the area of the large triangle is always greater than or equal to double the area of the small triangle. The equality holds only when the two sides are equal, which means Our original triangle must be an isosceles right triangle. What an elegant way to connect the deep properties of geometry with a simple principle from algebra. If you enjoyed unraveling this mathematical mystery with us, hit the like button and subscribe for more deep dives into math and science. Let us know in the comments what other puzzles we should explore next. Thanks for watching.